We will start our discussion on forced convection. In the limit of high Peclet number. Okay. Recall that the Peclet number is defined as the ratio of convective and diffusive effects, where Vc is the characteristic velocity, Lc is the characteristic length scale, and alpha is the diffusion coefficient. And in the limit of high Peclet number, you would expect convective effects to dominate compared to diffusive effects, or this is the limit of strong convection. Forced convection implies that the velocity field is already specified and it is independent of the variations in the temperature or concentration field. Okay. So, the velocity field is already known and it is now necessary to calculate the mass or energy balance equations to find out the temperature or concentration field and thereby the fluxes and then the average flux. Okay. The simplest case one can consider is the flow past a flat plate. Okay. So, I have a flat plate. Okay. In which I have t is equal to t infinity. Okay. Initially, for some distance the plate has temperature T infinity and T is equal to Tw, okay, the wall temperature, which is higher than T infinity. Okay. Put a coordinate system here, okay, at the start of the heating section, okay, x and z. Okay. And you have a flow past this flat plate. We will assume that this is a fully developed flow. Okay. We will assume that this is a fully developed flow, okay, past a flat plate. This is the velocity Vx, which is a function of z alone. Okay. And we would like to find out what is the heat flux and the heat transfer rate. Okay. So, the temperature conditions are T is equal to T infinity for z going to infinity, that is far from the plate. Okay. This is T is equal to T infinity far from the plate as z goes to infinity. T is equal to T infinity for z for x less than 0 and T is equal to the wall temperature, okay, at z is equal to 0 for x greater than 0. Okay. So, these are the three boundary conditions. Okay. Okay. So, there is one condition in the limit as z goes to infinity. I am assuming for the moment that this is an infinite medium. We will come back and examine this. Okay. And I want to know the correlation for the Nusselt number, assuming that the length of the flat plate, okay, is L. Okay. Okay. And T is equal to T infinity far away. Okay. So, I can scale the equations. Okay. In this case, it is a unidirectional flow and therefore, the equation, dynamical equation is Vx partial T by partial x. Okay. Vz is equal to 0. So, this is the only non-zero term in the convective, non-zero convective term in the equation is equal to alpha into partial square T by partial x square plus partial square T by partial z square. Okay. So, that is the conservation equation. Recall that the conservation equation was of the form divergence of V t. Okay. Let me take you back to the derivation of the conservation equation. Partial t by partial t plus divergence of V t is equal to alpha del square t. That was the conservation equation that we originally had. Okay. And this second term here, I can separate it out into two parts, okay, by differentiation by product rule. Okay. So, this will be T del dot V plus V dot grad T, okay. Okay, by differentiation by product rule. For an incompressible fluid, the divergence of the velocity is equal to 0, as we have just seen. Okay. For an incompressible fluid, the divergence of the velocity is equal to 0, as we have just seen, and at steady state the time derivative of the temperature is equal to 0. Okay. So, therefore, the equation becomes V dot grad T is equal to alpha del square T. Okay. For a two-dimensional flow, I can expand this out. Okay. Using the expression for the gradient operator and the velocity vector, this becomes Vx partial t by partial x plus Vz partial t by partial z is equal to alpha partial square t by partial z square plus partial square t by partial x square. Okay. So, that is the differential equation. In this particular case, it is a unidirectional flow. Okay. The flow is not always unidirectional, but in this particular case it is a unidirectional flow. Therefore, this term becomes 0 and I end up with this equation, okay, and I end up with this conservation equation. Now, I can scale. Okay. The only length scale that I have here is the length of the heated section. Okay. So, therefore, I can write x star is equal to x by L, y star is equal to y by L. Okay. And the velocity Vx can be scaled by the characteristic velocity. Okay. Average velocity in the case of flow through conduits and free stream velocity in the case of flow around objects. So, Vx star is equal to Vx by Vc. Okay. And T star I will scale the usual way, okay, minus T infinity by T w . Okay, so, that is the scaling for the temperature. Okay. So, that the scale temperature is going to be equal to T star is equal to 0 here, T star is equal to 0 here, and T star is equal to 1. Okay. So, that is going to be the scale temperature. And using this scaling, you can easily scale the equations and you will get Vc into L by alpha okay, Vx star partial T star by partial Z star is equal to partial square T star by partial So, that is the equation for the temperature, where this is the Beckley number based upon the characteristic velocity and the characteristic length. Okay. When this Beckley number is large, you can divide the equation throughout by the Beckley number, and if you neglect terms that are proportional to the inverse of the Beckley number, in this case, the solution that you get is Vx star partial t. Okay. My apologies here, this should be x. Okay. recall that it is V dot grad T, which will be Vx partial T by partial x plus Vz partial T by partial z. Okay. So, it is V dot grad T. Okay. So, it is Vx times partial T by partial x, and when I scale it, I will get a star over here. Okay. That is the approximation for Peckley number large compared to 1. Okay. That is the approximation for Peckley number large compared to 1. This just tells you that the velocity is that the temperature is a constant along streamlines. Okay. Vx partial T by partial x is the variation temperature along the streamlines, because the velocity Vx is in the x direction. So, this basically tells you there is no variation in the fluid velocity in the x direction. Okay. And upstream of the heating section, the temperature is just equal to T infinity, okay, or T star is equal to 0. Okay. The same fluid that upstream of the heating section was at T star is equal to 0 gets convected downstream. Diffusive effects are not important, and therefore, the temperature remains the same along a streamline. Streamlines in this case are lines of constant z. Okay. They are in the x direction. These are lines in the x direction. So, if T star is equal to 0, okay, upstream, and T star is independent of x, that means that T star is equal to 0 everywhere. Okay. It is equal to 0 at all locations, because it is the upstream fluid that is getting convected as it flows along, and we have neglected diffusion terms. So, this just gives you a trivial solution that T star is equal to 0 everywhere. Okay. And that does not satisfy this condition here. Okay. That does not satisfy the boundary condition here. Okay. If the velocity is just 0, if the temperature is just 0 everywhere, it does not satisfy the boundary condition. Physically, the boundary condition is not satisfied, because when we neglected the diffusion terms, we have reduced the equation from a second order differential equation to a 0th order differential equation in the cross stream direction. Okay. In the direction perpendicular to the surface, we have reduced it from the second order differential equation to the 0th order differential equation. Therefore, you cannot satisfy the boundary conditions which were specified for the original problem, because it was a second order differential equation. Physically, this is because when we neglect diffusion, right, the transfer from the surface to the fluid has to take place due to diffusion, okay, because there is no convection perpendicular to the surface. Okay. If there is a no penetration condition at the surface, there is no convection perpendicular to the surface. Therefore, transport from the surface to the fluid necessarily has to be due to diffusion, and when you neglect diffusion, there is no transport perpendicular to the surface. Okay. So, how do we remedy this problem? Physically, what is happening here? Okay. There is always diffusion from the surface, okay, but the material, the heat that diffuses from the surface is rapidly swept downstream due to the strong convection in the limit of high Peckley number. Okay. Any heat that is being transported from the surface gets rapidly convected downstream. That means that the energy, the disturbance to the temperature will be restricted to a thin region near the surface. Okay. The disturbance to the temperature has to be restricted to a thin region near the surface. The length scale in the cross stream direction is no longer L. Okay. The thickness of the region over which there is a temperature disturbance due to the surface is determined from the condition that convection and diffusion continue to be of equal magnitude in the limit as the Peckley number goes to infinity, okay, within this region. As the Peckley number goes to infinity, the thickness of this region decreases to 0 in such a way that the convection and diffusion are comparable within this region. So, when convection and diffusion are comparable, how do we solve the problem? Okay. So, the idea is that there is this smaller length scale delta, much smaller than L, over which there is a disturbance to the temperature field in the cross stream direction due to diffusion. Since this length scale is much smaller than L, we should scale the cross stream direction by delta instead of L, and select and the magnitude of delta is determined from the condition that convection and diffusion are comparable within this region. Okay. So, I will rescale my equation. Okay. X star is equal to x by L, Z I will call it as Z plus, okay, is equal to Z by delta. Okay. Delta is as yet unknown, it is determined from the condition that convection and diffusion are comparable within this region. What about the velocity v? We are focusing on a thin region close to the surface, okay, and if I expand out this region, okay, if I expand out this thin region, okay, this is the velocity 0, and within this thin region the velocity is increasing from the surface. Okay. At the surface it is 0 because there is a no slip condition at the surface. Okay. At the surface the velocity is 0 because there is a no slip condition at the surface. Close to the surface the velocity has to increase linearly with distance from the surface. Okay. So, very close to the surface, okay, Vx has to be equal to Vs prime times Z, okay, because it has to increase linearly from the surface and it has to be 0 at the surface, where this strain rate Vs prime, okay, is equal to dVx by dz at z is equal to 0. The slope of the velocity profile at the surface of the plate. Okay. So, Vs prime is equal to dVx by dz at z is equal to 0. Okay. Therefore, I can write this as Vx is equal to Vs prime into z. Okay. With this substitution, the equation becomes, okay, Vs prime z, okay, partial t by partial x star, okay, by L into partial t by partial x star. Okay. Z can be substituted in terms of z plus, okay, z can be substituted in terms of z plus. Okay. Therefore, I can write this as Vs prime z plus into delta. Okay. So, let me write that here. Okay. Vs prime z plus the Z plus is not the inner scaling in turbulent flow. This is the scaling for the boundary layer in a laminar flow close to the wall. Okay. So, this is equal to alpha into 1 by L square partial square t by partial x square plus 1 by delta square partial square t by partial z plus square. Okay, so, that is the conservation equation. Okay, so, let me write it a little bigger. Okay, so that is the conservation equation. And I divide throughout by the prefactor of the largest term on the right. Okay. Note that the streamwise diffusion term, is multiplied by 1 over L square. The cross stream diffusion term is multiplied by 1 over delta square. Okay, the cross stream diffusion term is multiplied by 1 over delta square. We know that delta is thin compared to the characteristic length scale L. So, 1 over delta square is much larger than 1 over L square. Okay. So, if I multiply by delta square by alpha, okay, so that the coefficient of the cross stream diffusion term is 1. Okay. Then I will get Vx Vs, sorry, this should be Vs prime And here you can see that streamwise diffusion can be neglected in comparison to cross stream diffusion, because the streamwise diffusion term in the x direction is multiplied by delta square by L square. Okay. Delta by L is small compared to 1. Okay. So, therefore, this term can be neglected. Okay. And then we have the term on the left. Okay. So, note that Z plus has been scaled so that it is order 1. Okay. Z plus has been scaled. The Z has been scaled by the thickness delta in such a way that delta decreases, but Z plus is comparable to 1 in the limit as the Peclet number goes to infinity. Okay. Therefore, I get Vs prime, okay, delta cubed by alpha L. Z plus partial t by partial x is equal to partial square t by partial z plus square. Okay. And for convection and diffusion to be of equal magnitude in the limit as the Peclet number goes to infinity, what I require is that this parameter, okay, this parameter has to be order 1. Okay. You can easily verify that this parameter is dimensionless. Okay. Therefore, I require that, okay, if convection and diffusion are comparable in the limit as the Peclet number goes to infinity, then Vs prime delta cubed by alpha L, okay, has to be order 1. That is, convection and diffusion have to be comparable so that the left and the right sides are comparable. Okay. Otherwise, if you just neglect the right side, there is no solution, there is no non-trivial solution. You just get the result that the temperature is independent of x. Okay. This implies that delta by L is goes as, okay, whole cubed, goes as alpha L square, no, where alpha is the diffusion coefficient, Vs prime is the strain rate at the wall. Strain rate is a derivative of the velocity with respect to z, and it has dimensions of inverse time. Okay. And because of that, you can easily verify that this is a dimensionless number. Okay. That is the ratio delta by L whole cubed. Okay. And what that implies is that delta by L is, okay, alpha by L square Vs prime whole power 1/3. Okay. Which is the Peclet number based upon V s prime, okay, okay, whole power 1/3. Okay. So, that is the scaling for this thickness delta in such a way that convection and diffusion are comparable in the limit as Peclet number goes to infinity, where the Peclet number in this case, okay, is based upon the strain rate and the length, okay, and this is equal to V s prime L square by alpha. Okay. It is not based on the characteristic velocity, but rather the strain rate close to the wall, because near the wall the velocity is determined by the strain rate times the distance, because the velocity has to decrease to 0 at the wall. Okay. So, that gives us a scaling for kindly make this correction, this has to be minus 1/3. Okay. In the limit as the Peclet number becomes large. Okay. In the limit as the Peclet number becomes large, this thickness becomes smaller and smaller, comparable to Peclet number to the minus 1/3, in such a way that convection and diffusion continue to be of equal magnitude. The thickness decreases, the Peclet number increases in such a way that convection and diffusion continue to be of equal magnitude within this layer in the limit as the Peclet number goes to infinity. Okay. So, that gives you that the boundary layer thickness has to scale as P power minus 1/3 in the limit as P goes to infinity, where this Peclet number is based upon the strain rate and the length of the plate. Okay. Now, I told you that when in the limit of high Peclet number you can neglect streamwise diffusion in comparison to cross stream diffusion, because in the cross stream direction the length scale is small, it is much smaller than the length scale in the streamwise direction. The gradient in the cross stream direction is much larger, okay, and therefore, you can neglect cross stream diffusion streamwise diffusion in comparison to cross stream diffusion. Okay. So, in this case the equation for the temperature field will just reduce to V x partial T by partial x is equal to alpha times partial square T by partial z square. Now, how do I solve this problem in order to determine the temperature field as a function of x and z? Okay. So, as you can see in this boundary layer I have included only streamwise diffusion and streamwise convection and cross stream diffusion. Okay. So, within this boundary layer I have included only diffusion in the cross stream direction okay, and convection in the streamwise direction, okay, and convection in the streamwise direction. Okay. And because of that I have neglected the streamwise diffusion term, which is much smaller than the cross stream diffusion term, because the temperature gradients, the length scale is small and therefore, the temperature gradient is large. Okay. So, the length scale is much smaller than the characteristic length scale, and the temperature gradient is much larger than the temperature gradient in the streamwise direction. Okay. So, that is the reason I have neglected the streamwise diffusion and I have included only the streamwise convection and the cross stream diffusion. This is for a unidirectional flow. Okay. In general, the equation would be V x partial T by partial x plus V z partial T by partial z, okay, is equal to alpha times partial square T by partial z square. Okay. We will come back and examine the conditions under which this equation is valid. For the particular case that we are considering, there is no velocity in the z direction. So, this term just becomes equal to 0. Okay. So, this term just becomes equal to 0. How do you solve this equation? Okay. I will start that in the next lecture. Okay. We will do that using a similarity transform. The method for solution is similar to the similarity transform we had done for unsteady problems. except that this is based upon a physical picture that there is a balance between streamwise convection and cross stream diffusion, and therefore, the temperature at the location x of this heated plate can depend only upon the distance from the start of the heating section and not on the total length of the plate. I will continue this in the next lecture. I will see you then.